Thank you for introducing me. I'm happy to be able to talk here. The title of my presentation is the Attacks Against FESTA Without Input Validation or Constant Time Implementation. First, I provide a quick summary of our result. There's an isogen-based scheme named FESTA. It's proposed by the Basel and Minor and Pope in AJ Group 2023. And our result is an attack for the FESTA, or I should say the FESTA variants, if there is no input validation or constant time implementation. Okay, so I first I explain some background in this study. First, I introduced the elliptic curve, and elliptic curve is a curve defined by the equations, and it has some many nice properties. And one important property is it has a commutative group structure. And from P and Q, we can define P plus Q as in this figure. And this operation provides a commutative group structure. And I also introduced a property about the n-torsion subgroup. And if n is prime to the P, then an n-torsion subgroup En is isomorphic to Z over N squared. And we use this property for construction of FESTA. And next, I introduce isogeny. Isogeny is a map between two active curves, but it has also some properties. And first, then it is a morphism. So it can represent by using the polynomials. And it also a group morphism. So this map is compatible with group structure of empty curves, and this is a surjective map and with a finite kernel map. And I also introduced some related concept of isogeny. First, I defined the degree of isogeny, and I defined degree of isogeny as a cardinality of the kernel phi. And from the definition of isogeny, kernel phi is always a finite group, so a degree of phi is always a positive integer. And I also introduced the dual isogeny of phi. And if you have the isogeny phi from E1 to E2, we always have the isogeny E2 to E1, and such why the compose of the phi and phi hat is multiplied by degree phi map. And if we have the empty curves and isogenies, we can construct the graph. And this figure shows a very small example of the graph, but the size of the graph is about the P over 12. So if P is extremely large, then this graph is also extremely large. The vertex of this graph is empty curves and edges are isogenies. And from the side of the view of this graph, then isogeny is related to the path in this graph. And the degree 5 is kind of the length of the path. And the dual isogeny is kind of the backtracking path of phi. And if we consider the graph, we can find a symmetry relation. First, we can compute the isogeny from an empty curve E and its finite subgroup G. Then we can compute the isogeny phi from E to E prime with kernel is equal to G. And this computation corresponds to the random walking in the isogeny graph. And on the contrary, we have the mathematical problem named the isogeny problem. It is related to the path finding problem in the isogeny graph. So if we have the isogenous empty curves E and E prime, so there's a pair of empty curves, but we know there's a isogeny between them. Then the isogeny problem is a problem compute isogeny phi from the E and E prime. And this problem is considered as hard even using a quantum computer. The isogeny-based cryptography is cryptography based on this asymmetric relations. But however, it is quite hard to construct the isogeny-based scheme by using isogeny problem itself. So there's many weaker variants of isogeny problems. The first famous variant is CSSI problem. It is proposed in the PT 2011. And I remind that then the n-torsion subgroup is isomorphic to Z over n squared. And so there's a basis of En. Then I denote one basis and P and Q. And then CSSF problem is a problem that we compute phi from En pi EPQ and E prime pi B pi Q. So in this setting, we know the exact image of torsion points. And this problem had been considered as hard about 10 years. However, recent research reveals the algorithm to solve this algorithm in polynomial time. And we call this algorithm the SIDH attacks. So by using this algorithm, we can break SIDH or site. So to construct the isogeny-based scheme, we need a harder variant, the isogeny problem. And today I introduced, I explained this problem. It's highly related to the construction of FESTA structure function. And this problem also compute isogeny phi from the E and E prime and PQ and the point of the basis of the E prime. And, sorry, and there's some group of E Q prime. But this point P prime and Q prime asked by special matrix A. Here, and B is a commutative subgroup of general linear group Z over to the 2B. And then P prime Q prime, the masked by hidden matrix A belongs to this commutative subgroup. And this problem, there's no one can find the algorithm to solve this problem so far. Okay, then I explain the construction of the FESTA structure function. And this diagram shows the structure of FESTA, and there's four FT curve and four bases of the n-torsion subgroup and three isogenies. But each point is masked by hidden matrix, and P prime Q prime are masked by A, and P1 Q1 and P2 Q2 are masked by B. And A and B belong to the same commutative subgroup of general linear group. So if you don't know A and B, you can not compute the isogeny phi 1 and phi 2. But in this structure, we can find a trapdoor. And if we know a matrix A, first we can compute the P2 prime and Q2 prime as degree phi 1 times A inverse times PQ2 Q2. Then since AB equal BA, because A and B belongs to the fixed commutative group. So and AB equal BA. So by direct computation, we can find the P2 prime and Q2 prime is equal to the phi to phi at phi 1, P1, Q1. So if you know the A, you can obtain the precise images of the torsion points. So it's the same setting for the CSSF problem. So by using SSH attacks, we can compute the hidden isogeny and phi 2 and phi 1. So one who knows A can obtain the phi 1, phi 2, and B. So this is a trapdoor of this structure. And by using this, we can construct a trapdoor function. And the public key of function is the E and PQ and E prime, P prime, Q prime. And secret key is A, and input is phi 1, phi 2, B. And output is E1, P1, Q1, E2, P2, Q2. And it's hard to compute inverse map if you don't know the secret key A. And this is the construction of FESTA trapdoor function. And I also introduce the input validation. It is not essential for constructing the FESTA trapdoor function, but it's quite highly related with our two attacks, so I explain it. If the matrix B does not belong to NB, and then the recipient reject phi 1, phi 2, B. So generally, B should be belongs to the fixed subgroup NB. Okay, so then I explain about our result for the attack for FESTA variants. And first, I explain the attack scenario of the attack scenario. First, the sender Bob tried to obtain the secret key, the recipient Alice, and he first sent an collect output to Alice, Then there are two cases happen. The first case is an iris succeeds in using the SSH attacks. And the second case is iris fails to use SSH attacks. In other words, in the first case, iris obtains the precise image point under hidden isogeny. But second case, she couldn't get the precise image points. Then we also assume that Bob can distinguish the above two cases. So in other words, Bob had access to an O prime. It outputs 1 if Alice succeeds in using SSH attacks, or if it outputs 0 if Alice fails to use SSH attacks. Then finally, by using this Oracle prime, he obtains A. So this is an attack scenario of the our result. But also, of course, there's a gap in this scenario. The first gap is how do we construct the Oracle prime? The second gap is how do we obtain A from this Oracle? So this theorem solved the second gap. If there's Oracle O, it outputs 1 if A and B1 equal to B2A, and if it outputs 0 if AB1 it does not equal to B2A, then there's a polynomial time algorithm to compute A. So by using this Oracle, we can solve the SIS problem. And it is easy to see the relation between the O1 and O prime. And so they both generate incorrect output by using B1 and B2, and they put this incorrect output to O prime. Then the result is same as O. So if we can construct the O prime by using this theorem, we can solve the SIS problem. However, there is a problem in how do we construct the Oracle prime. Why this is a problem? It's because in this theorem, B1 and B2 is not necessarily belongs to MB. So by using the input validation, and Iris can reject this incorrect output. So O prime is not the decryption Oracle. So we need more some stronger assumption for this attack. Then I explained how to construct O prime, and this diagram shows the computation of Iris. The first she uses SSH attacks. Then if it fails, she has bot, and if it succeeds, she computes the phi 1 phi 2 B and use input validation. Then if it fails, she has bot, and if success, and she has put phi 1 phi 2 B. And the first situation we can control prime is there's no input validation. And there are two examples that this case happened. The first case is the long use of the FESTA transfer function. So FESTA transfer function is implemented battery, and there's no input validation case. And the second case is other scheme based on the SIS program. For example, the iSkiver signal is does not have the input validation. So for this scheme, we can use our attack. And the second situation is there's no constant time implementation. The computation of the phi 2 and phi 2 B is quite costly. So if it does not have the constant time implementation, by measuring the computation time, we can distinguish the two cases, then SSH attack success or future case. Okay, so this is a summary of our results. So there's a for FESTA variant if it has no input validation or constant time implementation. So if you use FESTA, you need to care about the input validation and the constant time implementation. Thank you for listening. Any questions?
Thank you. Any question? Okay, I have a quick question. You mentioned your attack to obviously FESTA, but it's associated with CIST problem. Then you also mentioned that there are some other algorithms based on CIST, and you give to you. Actually, your attack affected to those schemes or not?
Yes, but basically we use some free security transform or something for them. So if after transform, we can use this attack, but the train version we can affect it to this scheme.
Okay, thank you. Any more questions? All right, let's thank the speaker again.